Okay, 4.2 uniform distributions. So in continuation of our study of probability distributions, this is going to be one of the types that we're going to be looking at in this section. So uniform distributions. So what's a uniform distribution? Well, these are distributions where all outcomes are equally likely in a single trial. The probability is equal to 1 over n, and n is the number of possible outcomes in the experiment. And all probability distributions must sum to 1, since they all include all possible outcomes. Okay, so that has been already a given. All the probabilities have to add up to 1 or 100%. So let's look at this example. A calculator has been programmed to generate a random number between 1 and 5. Classify the distribution. Well, each random number is equally likely. So this is a uniform distribution, so it's equally likely. And that's key because it's uniform only if everything is the same. And what we're talking about is the same is the probability. Okay, so this is a uniform distribution. So calculate the probability distribution and sketch a graph of the distribution. So if you remember from the last lesson, when we do probability distributions, we graph them using histograms. So we're going to create a histogram for this uniform distribution. Before we could do that, let's fill in the table and find these probability values. So you have a random number generator, and your variable is going to be x, and that random number generator is going to generate a number between 1 and 5. So my x is going to be one of these outcomes, which could be 1, 2, 3, 4, or 5. Now there are 5 outcomes in total, so n is equal to 5. And the probability, since they are all equally likely, is just 1 out of 5, right? 1 out of 5, which is 20%. So you have a 20% chance to get any one of these numbers from the random number generator. Okay. Now when I multiply, so we're going to be doing expected value calculations as well. So it's also a good idea to find out x times the probability. So let's do that. So we'll just take the number in the first column and multiply it by the number in the second column. So 1 times 1 over 5 is just 1 over 5. 2 times 1 over 5 is 2 over 5. Then we have 3 over 5, 4 over 5, and 5 over 5. Okay, so let's do our probability distribution. So let's graph the probability versus the number x. So for number 1, we have 20%, and they're all going to be uniform, right? So all of them are going to be 20%. So I'm just going to draw a line all the way to the end here, and just draw. It's still a histogram, so you have to draw these bars and show that every single bar is representing a probability of 20%. Okay, and so there is our probability distribution. It's a uniform, so all those histogram bars are going to be at the same level. Okay, so let's calculate the expected value or expected outcome of this distribution and interpret its meaning. So the expected value E of x is equal to sigma, which is the sum of every single x value times its probability. Okay, so that's what we found in the table here. So 1 over 5. We're going to keep adding all of those values together. So 2 over 5 plus 3 over 5 plus 4 over 5 plus 5 over 5. Okay, and then when I sum all of those numbers up, I get 15 over 5, which is equal to 3. So what does this mean? This 3 is the expectation. So the expectation is 3, meaning the predicted average value of a random number will be 3. Okay, it's just the average. So therefore, let's write this down. So the expectation is 3, meaning the predicted average value of the random number will be 3. But remember, it's an average, right? It's because we compared this to when we did weighted means, and weighted means are just an average. So an expected value is just like a weighted mean, and so it is an average. So the average number that will be generated on that random number generator is 3. And it doesn't necessarily mean that they will automatically show up 3, it's just that that's the average. Okay? Example number 2. Consider a simple game in which you roll a single die. If you roll an odd number, you gain that number of points, and if you roll an even number, you lose that number of points. What is the expected value per the roll? Okay, so if I roll a 1, I expect to gain 1 point. If I roll a 2, I expect to lose 2 points because it's an even number. And here 3 is an odd number, so I'm going to gain 3 points, and then minus 4 points, plus 5 points, and minus 6 points. Okay, so if it's even, you lose. If it's an odd, you win. So what's the expected value of the number of points you expect to roll get per roll? So expected value, E of x, is equal to the sum of every x times its probability. And so x in this case is going to be the number on the die. Okay, so it's the number on the die up here. So I take the number 1 multiplied by its probability. So what is it? What is the probability of rolling a 1? Actually, the probability of rolling any number on this die is, I'm sorry, I made a mistake here. X is not the number, x is the number of points. That's what I had here. X is the number of points. So I'm going to take the fact that I can gain 1 point and find the probability of gaining 1 point. And that probability is 1 out of 6. Okay. Remember, the reason why it's points is because the expected value is expected number of points. So I'm using points as my x. Okay. It doesn't matter what the die number is. The die number tells us how many points we're going to have. And that's what I'm going to be using. Okay. So 1 times 1 over 6. Now, if I'm going to lose 2 points, well, I'm going to be minus 2 instead of plus 2. And the probability of that is 1 out of 6 as well. Then I'll have plus 3 points for the next x value. That's 1 out of 6. I'll have minus 4 points, and that's 1 out of 6. And I'll have plus 5 points, which is 1 out of 6. And minus 6 points times 1 out of 6. Okay, altogether I have 1 out of 6 if I factor it out. 1 minus 2 plus 3 minus 4 plus 5 minus 6 in brackets. And in total, that's going to equal negative 0.5. So this negative 0.5, that is our expected number of points per roll. So the expected points per roll is negative 0.5. This is the average number of points you could expect to get when you roll that die. So part B, a fair game will always have an expected value of 0, right? So like an even number of ways, kind of like if the average is 0, there's like just as many ways to win as there are many ways to lose. So if this is not a fair game, right? Because your expected value is less than 0. So this is not a fair game since the expected value of x is not equal to 0. The game is to the advantage of the dealer. Since the player loses 5 points for every roll, or 0.5 points, I should say, per roll. Okay, so let's give your turn. Okay, so here a spinner has 8 equally spaced sectors from 1 to 8. In a game, a player wins points equal to double the sector's face value if a power of 2 is spun. For all other spins, the player loses the face value of the spin. Is this a fair game? So I want you to take a moment, pause the video, and see if you can figure this one for yourself. Okay, so hopefully you had a chance to do it. Let's take it up. So spinner has 8 equally spaced sectors from 1 to 8. Here they are, from 1 to 8. 8 to if your spin is from one of these sectors, 1 to 8, you're going to get a certain number of points. So the win points equal to double the sector's face value if a power of 2 is spun. Okay, so for all other spins, the player loses the face value of the spin. So you have to check which of these numbers is a power of 2. Well, 1 is a power of 2 because it's 2 to the power of 0. 2 is a power of 2 because 2 to the power of 1 is 2. And then you have 2 squared, which is 4, and then 2 cubed, which is 8. So it's these 4 sectors that are going to award you points. And how many points are they going to award you? It's double the sector's value. So if this sector is 1, then the points you win is 2. If this sector is 2, the points you win is going to be 4. And I'll put plus signs to say that we're winning these points. And then here I'll have 8, and then here I'll have plus 16. For every other area, you're going to lose points. Okay, so for all other spins, the player loses the face value of the spin. So for sector number 3, you lose -3. Here you lose -5. Here you lose -6, and here you lose -7. Okay, so is this a fair game? So let's calculate its expected value. So e to the x equals x times p of x. So I'm going to take each of these points, so I can have 2 points and have a probability of 1/8 because there's 8 sectors equally spaced. So you have a 1 out of 8 chance to get those 2 points. Then I can also get the 4-point win, so that's 1 out of 8 as well. Or I could land on sector number 3, which would make me lose 3 points, so it's -3, which is times 1 out of 8. I could gain 8 points for landing on sector 4, and that's again 1 out of 8 chance. And then I go -5 for the 5th sector, and then -6 for the 6th sector, -7, and plus 16 for the last one. That's the winning one. Okay, so I take all these 1/8 multiplied by their numbers there, and I add them all up, and you'd find the total would be 9/8, or 1.125. Okay, so again, not a fair game. In this case, it is favoring the player because there's your expected number of points per spin is going to be 1.125 points. So therefore, this is not a fair game since the expected value is not equal to 0, but it does favor the player. Okay, example number 3. The summer camp has 25 canoes, 7 4.6 meter canoes, 10 5 meter canoes, and 4 5.2 meter canoes, and 4 6.1 meter canoes. You might want to take a moment and reread that part. All right. Canoes are assigned randomly for campers going on a canoe trip. Show the probability distribution for each length for the length of an assigned canoe. Is this an example of a uniform probability distribution? For a canoe length of 4.6, the probability of getting that canoe is, well, you have how many of them? 7 of them. So 7 out of how many canoes in total? 25. So 7 out of 25, which is 0.28 or 28%. The 5 meter canoe, well, it turns out we have 10 of those. So 10 out of 25 equals 0.4. And 5.2 meter canoes, we have only 4 of those. And that's 4 out of 25, which is 0.16. And here I have 4 out of 25, which is also 0.16. So if I try to graph these, so 4.6 goes to 0.28, so I have the first bar over here. For 5, I'm going to have one going all the way to 0.4. Oops. Okay, and I'm roughly drawing this, so it's not going to look that great, but hopefully you'll use a ruler in your notes. So for 5.2, I have 0.16, so somewhere up here. And for greater than 6 or 6.1, I have 0.16 again, so it's going to be somewhere up here. Okay, and again, the graph, the way it's set up, there's a bunch of different canoe lengths, but we don't have all those numbers, so we don't get a histogram here. Okay, but we don't even have a uniform distribution, by the way, so no, and it's not uniform. Okay, so what is the expected length of an assigned canoe? So let's calculate the expected value. E to the x equals sigma x times p of x. And that's equal to, well, we take 4.6, so that's my x value, times its probability, 0.28. Add 5 times 0.4. You add 5.2, and you multiply that by 0.16, and you add 6.1, and you multiply that by 0.16. Altogether, you get 5.1 meters. So therefore, the expected length is 5.1 meters long. Now, does that mean there's a 5.1 meter canoe? No. Again, expected value is just an average. Okay, and that ends our lesson for 4.2.